record. Okay, is everybody comfortable with the Gaussian integral?
Yes.
There's only three of you,
Yes.
Sebastian, Sergio? Okay, good. So we can calculate this Gaussian integral. It comes out to be the square root of 2 pi, and that's just this integral we want to calculate, evaluated at I equals 0, so we kill off this quadratic piece here. But we really do want this quadratic piece. The problem is turning on this quadratic piece means you can't calculate this integral as a closed function, exactly. So what you need to do is Taylor expand. Now, you would look at this and you would say, well, okay, the simple thing to do here would be to split the exponential of the sum into the product of two exponentials. The first one we already know. The second one, we could just consider making it an expansion in lambda. That's kind of what we're doing, except we're developing something more sophisticated. And this is a general mechanism, general machinery for perturbation theory, right? So what we're trying to do here is more sophisticated, and when you look back at it, you're going to be appalled at how much effort it's going to take to get a simple answer like we're going to get at the end of this. And I'd like you to keep in mind that our point is not the answer. Our point is the process. So we're really trying to develop the process in this example. Okay, so keep that in mind. Don't judge me for picking a ridiculously difficult method for solving what looks to be a straightforward thing. Okay, so again, just to remind you here, having integrated out the x dependence, I is really a function of lambda. And in general, we can just think about it as a function of lambda. So we're going to need to integrate, differentiate, etc. Okay, and I want you to just think about the fact that it's an integral is by the by. It's just a function of lambda. Okay. So then I said last time that instead of considering this I, I'm going to consider instead another integral, which is also a perturbation away from the Gaussian integral. Instead of considering e to the minus half x squared, I'm going to consider e to the minus half x squared plus some linear perturbation. So I add some term that's linear in x to this problem. The coefficient of this guy here, again, integrating out x, means that this integral, which I'm calling a, is a function of this coefficient, which we'll call j for traditional reasons. And in the language of quantum mechanics and quantum field theory and string theory, this j is called a source term. In fact, the whole j times x is called a source term. And so this is perturbing this Gaussian integral by a source. Is that clear? All I said was some notation. Okay, there's nothing conceptually difficult here. So we add this linear perturbation to the Gaussian. Okay, and then we went through the exercise and showed that this guy a is really just a function of j, and as a function of j, I can do everything else that I do to functions that are differentiable. I can differentiate it. In fact, if I wanted, I can integrate it. And for those of you who may have seen this before, you will recognize that this is nothing but Leibniz's rules for differentiation and integration under the integral sign. And so if I do some subsequent differentiations and I continue with this, I'll find that I can then resum these terms on the left-hand side into any differentiable function, in this case of the derivative operator d by dj. I'm differentiating with respect to the source. Inside the integral on the right-hand side, I can do the same resummation, same coefficients, and it should resum. If the left-hand side resums to f, the right-hand side will resum to f, except on the left-hand side, I have an operator, a functional operator of the derivative operator. Here, that same functional form carries through as a function of x. Can everybody see that? You happy with this?
Yes, I have a little question from other thing.
Yeah.
We know that the quartic term is not calculable exactly from the semi-classical approximation process we followed. We did the Taylor expansion and we had higher order terms. And from there, we know that quartic term is not exactly calculable. Or is there any other way to see this as well?
No, if you're thinking in terms of the quantum mechanics problem or the quantum field theory problem, then yes, that's a good place to see it. I'm actually just doing an integral now. And my statement to you is that this integral I here, doesn't have a closed form solution.
Yeah, so how do you know that? That's my question.
you know it by some theorems in analysis.
I see. Okay.
So
yeah,
this,
but not like
there's no
we haven't taken anything. Yeah.
Right? This is a strictly
Okay.
mathematics problem. You can pick up some advanced textbooks in analysis, and there's a class of integrands that you can show doesn't have a closed form solution. By closed form solution here, of course, I mean the following. It's a definite integral. Okay, so closed form solution means I can just write down a number. It should just be a number. I'm integrating out any x dependence. Okay.
Yeah.
Right. So what I mean here is that what I'm lacking is if I take away the minus infinity to infinity part, but just write down an indefinite integral. There is no indefinite integral to this. In fact, there's no indefinite integral to the Gaussian either. But I know how to calculate the Gaussian, square root of 2 pi in closed form. I can't do that with the lambda. You with me?
Yeah. So if we remove the limits, even then we can't do this one.
If you remove the limits, there's no, I mean, e to the minus x squared doesn't have a closed form solution, right? I mean, you can write down something, but it's what we call a quadrature. It's an integral representation. The point is you can't do that integral in closed form.
Yeah. Okay.
Okay. And this lambda x to the 4 part kind of builds on that class of functions that you can't write down a closed form solution for the indefinite integral. But even when I have the definite integral, I can't do the same kind of tricks that I could do to write down the Gaussian. Remember, if you recall what you would have done when you first encountered Gaussian integrals and you wanted to calculate the area under the Gaussian, what you did was to consider the product of two Gaussians, go to the complex, consider the product of two Gaussians, convert that to a double integral, then go to polar coordinates, and there you found that the Jacobian in going from Cartesian coordinates to polar coordinates contributes exactly that factor that you need to make a change of integrals, to make a change of variable in the integral that allows you to solve it, right?
Yeah.
Can't do that anymore with this x to the 4 term.
Okay.
Okay.
Yeah, thank
you.
All
right. So this is I said the last time that if you go and look at some quantum field theory textbooks, this is what some people call the fundamental relation in quantum field theory. Everything that we do everything that we do perturbatively stems from this particular relation here. Okay. So now I want to use this to calculate the integral that we started off calculating. So to do that, I'm going to make the following guess for what my function is that I want to work with. And in particular, I want to choose, so let's choose f of this d by dj, the derivative operator. I'm going to choose it to be the following exponential operator. It's going to be the exponential of minus lambda over 4 factorial d by dj to the 4x. Right? I'm choosing this. Let's see what the consequences of this is. If I choose this to be the case, then the following is true. Okay? Then that fundamental relation that I wrote down becomes e to the lambda over 4 factorial. This factor of 4 factorial that I insist on dragging along for the ride here will become apparent why I'm doing that in a little bit. Acting on this source, a of j, is equal to the integral from minus infinity to infinity, integrating with respect to x, of e to the minus, remember what happens, the same functional form, except where I see the d by dj, I've got to replace it by x, so that becomes x to the 4. And then I have e to the minus a half x squared plus jx. Of course, I can always write this thing as the integral from minus infinity to infinity of the exponential minus a half x squared minus lambda over 4 factorial x to the 4 minus jx. Okay. Well, that looks pretty much like the integral we want, except for this factor of j here. But if I just set j equal to 0, then it is the integral that I want on the right-hand side. On the left-hand side, I have this e to the minus lambda over 4 factorial d by dj to the 4 a of j. In other words, the integral we want, this integral that we want, I of lambda, is nothing but the exponential operator minus lambda over 4 factorial d by dj to the 4 acting on a of j, all evaluated at j equals 0. Can you see that? Okay, so in other words, all that we need to do in order to evaluate the integral a of j is take its derivatives, and that'll give us an estimation of I order by order in lambda, right? Provided I can actually evaluate a of j. So let's make a note of this. So all we have to do is evaluate a of j and its derivatives. And that'll give us an estimate then of the integral I of j to each order in lambda. Okay. Fortunately for us, we can actually evaluate a of j. So to evaluate a of j, we do the following. Before I go on, can anybody tell me why we can evaluate a of j? Sebastian?
Isn't it just a standard Gaussian integral?
Cool, that's exactly what it is. So it is just it's not quite a standard Gaussian integral, it's a shifted Gaussian integral. Unless, like, you know, you're Russian kindergartner or something, then it's a standard Gaussian integral. So this is just integral dx e to the minus a half x minus j squared times e to the plus a half j squared that I needed to add to this in order to complete the square. Okay, so if you complete the square, this is, as Sebastian pointed out, just a standard Gaussian in X. So in fact, a shifted Gaussian. And to accomplish the shift, I needed to add this exponential piece here. The Gaussian integral, I can do that just comes out to be root 2 pi, and the remaining bit is just the exponential. Let's just write it like that, e to the j squared over 2. Okay, so great. Now we have a closed form expression for this a of j, the source integral that we're considering. So let's use this to estimate then I of j. So if I expand, so expanding in lambda, we find then that I of lambda is, expanding the exponential, is 1 minus lambda over 4 factorial times 4 derivatives. So that means d by dj, d by dj, d by dj, d by dj, plus higher order terms. That's the expansion of the exponential, times acting on a of j. And then remember, at the end of the day, I want to set j equal to 0 in order to touch base with the integral that we want. So let's act with each term. So if we act with each term, this is, the first term is a at naught. That is a of j evaluated at j equals 0, minus lambda over 4 factorial, 4 derivative operators acting on a of j evaluated at j equals 0, plus terms that are going to be at least order lambda squared. This first term is already evaluated. We know what a of j is. A of j is the square root of 2 pi e to the j squared over 2. So a of naught is nothing but the square root of 2 pi. The second term, if I say it out in words, we're going to need to take 4 j derivatives and then set j equal to 0 everywhere. Now, any term that has fewer than 4 j's, when I take 4 j derivatives, those terms are going to get killed off. Any term that's got more than 4 j's, once I've taken the 4 derivatives and then I set j equal to 0, all of those terms will get killed off. In other words, the only terms that are going to survive in this expression, in the second term, are terms that are quartic in j. Can you see that? This is the absolute crux of simplifying this.
Yes.
Sergio, you good?
Yes, Prof, I'm good there.
Good.
Because you're taking 4 derivatives, it's fine.
Taking 4 derivatives and I'm setting j equal to 0. Anything with less than 4 derivatives will die off by differentiation. Anything with more than 4 derivatives, after I've differentiated, there'll still be factors of j floating around. All of those guys will go to 0. Okay? So if I expand a of j about j equal to 0, let's see which of the terms has the quadratic piece. So expanding a of j in the Taylor series about j equals 0, we get the following. A of j is square root of 2 pi times, this is coming from the exponential, 1 plus j squared over 2 plus j to the 4 over 8 plus terms that are higher order in j, right? So that if I take 4 derivatives, d4 by dj to the 4 acting on this a of j. And then I set, okay, that's going to be 4 times 3 times 2 times 1, which is what we call 4 factorial, divided by 8 square root of 2 pi plus terms containing at least one j. Okay. So if we do what I said, it follows then that the integral that we want I of lambda is equal to the square root of 2 pi times 1 minus lambda over 8 plus higher order terms, which I haven't corrected for. So that's the first correction in lambda, the first subleading correction in lambda to this integral. So everybody happy about that? Good. So you may well argue that this was a lot of work for a relatively straightforward integral. And one way to convince yourself of this is to check this another way. So here's an exercise for you. Okay. But again, we're never interested in the answer. We're interested in the process. And to illustrate this, I'm going to use this exact same method. So again, what I did just now was calculate this for a straightforward one-dimensional integral. So I want to use exactly the same method to do something less trivial. And the less trivial thing that I want to do is to work out the lowest energy level of the anharmonic oscillator. So now let's use the same method to work out the lowest energy level, the ground state energy of an anharmonic oscillator. You might ask, what is an anharmonic oscillator? An anharmonic oscillator is something that's not a harmonic oscillator, but close to a harmonic oscillator. So it's harmonic oscillator plus some perturbation typically. In particular, I want to consider a quartic perturbation so that we can touch base with what we've just done. And in fact, we've done most of the hard work already, so we can more or less read off the result. Any questions? So this calculation starts off really from the partition function, which I want to remind you, the partition function is a function of the inverse temperature beta, and it is the sum over states j of e to the minus beta times the corresponding energy of that state j. Okay, so if I look at this, each state is going to give an exponential contribution to the partition function, not just any old exponential contribution. It's going to give a decreasing exponential contribution as I go higher and higher in energy levels. In other words, in the limit of large beta, or small temperature, the biggest contribution to the sum is going to come from the lowest energy, or the ground state energy, E0. Okay, can you see that? Okay, good. So to extract the ground state energy, we note that if we take the partition function, take its logarithm, so we take log of z, divide that by a factor of beta, and then take the limit as beta goes to infinity, then what we will get is not the ground state energy, but actually minus the ground state energy. And so if I add a minus sign to that, then I get precisely the ground state energy. So to extract the ground state energy from the partition function, what you need to do is take the logarithm of the partition function, divide it by the inverse temperature, take the limit as the inverse temperature goes to infinity, or equivalently as the temperature of the system goes to 0, and that is the ground state energy. Okay. So, okay, that's good, but it kind of still involves us doing some work, and the work that we'd have to do here is in computing the partition function. And if you know anything from statistical mechanics, then you would know that computing partition functions in general is a non-trivial task, essentially because I have to evaluate these energy levels, EJ here, which involves diagonalizing a Hamiltonian. Typically, your Hamiltonian is a large n by n matrix. And so diagonalizing this matrix, diagonalizing any matrix, you would understand is an NP-hard problem in computer science lingo, which means that it's very difficult to compute as the size of the matrix gets bigger and bigger. So we would like to do better than just writing down this expression. And it turns out we can, because we in fact have an expression relating the partition function to the path integral. And it goes like this. So recall then that the Euclidean path integral that connects the ground state 0 at time t equals 0 to the ground state at time t equals 0 to the same ground state at some later Euclidean time beta. So I'm calling it Euclidean here because I've made an analytic, I've set t equal to minus I beta, and then I've made an analytic continuation to tau, which is beta, and that gives me the Euclidean path integral. And the Euclidean path integral between those two states, the ground state, which I'm denoting 0, is just that state evolved in Euclidean time and projected back onto the ground state. Well, now if I insert a resolution of the identity in the states J, which are eigenstates of the Hamiltonian, then I get e to the minus beta h sum over J of J outer product J on 0. In other words, using the fact that J are eigenstates of the Hamiltonian. Sorry, let's a little down. Using the fact that the J are eigenstates of the Hamiltonian operator, this is just the sum over J of e to the minus beta ej times phi j naught phi j of naught bar, where I'm denoting wave functions of the Hamiltonian by this phi j. Well, here again, in this sum, the ground state dominates in the large beta limit, which means that we can extract the ground state energy again as minus the limit as beta goes to infinity of 1 over beta times the log now of the Euclidean path integral between 0 beta and 0 0. And as an exercise, let's just note this. This is an important relation. So this is how we extract the ground state energy if we know what the path integral is. And the interesting thing about this is that the path integral is easier to compute than it is to diagonalize, computationally speaking, than it is to diagonalize the Hamiltonian. Okay, because we have an expression for how to calculate the path integral in an integral representation, and then we can apply all our perturbation theory to computing that integral. So let me just give you an exercise here, because you really ought to convince yourself that the following is true. So here I'd like you to argue that in the large beta limit, the difference between log z over beta and log ke over beta goes to 0. Okay. I want to make one more point and then we can stop for the day. So here, this ke of 0 beta 0 0 is simply equal to the path integral of x of tau e to the minus the Euclidean action of x, where the Euclidean action SE of x is given by the Euclidean action SE of x is given by the integral from 0 to beta with respect to tau of m over 2 dx by d tau plus v of x. Okay. And my claim is that this is a much easier thing to calculate than is diagonalizing the Hamiltonian for a larger matrix, for a large matrix. Nitin, what's the question? Why we need to do?
Yeah, why we need to take the beta going to infinity limit?
So we can actually kill off the, because I want to take the limit as beta goes to infinity because I want to get no other contributions for the higher order terms. If I send beta to infinity, then because there's this 1 over beta multiplying all the other terms, that 1 over beta kills off all the other terms.
No, I mean in the E naught.
Yes, so do I.
So if I choose J as 0, then I don't need to do this, right?
Where's J?
So we have sum over J e to the power minus beta J.
If you choose J equals 0, but my point is that I want to extract E naught from this expression for Z.
Okay, so you mean that we don't know the energies, but we do know the partition function.
Correct.
Okay, got it.
Okay. Very good. Okay, so that's all I wanted to say for today. So next time we will make this concrete. Pick a particular V of x to give the anharmonic oscillator and do the computation to extract the ground state energy. Okay, so that's going to take a bunch of work. But as I said previously, we've done most of the work in this story. Most of the work in the story already comes from this one-dimensional integral I of lambda that we had. Okay, so we have computed I of lambda perturbatively, and we're on our calculating corrections to E naught for perturbed quantum harmonic oscillator.
Sorry, Prof. Did you write something for where SE of x? Is there supposed to be an equals after there? On the note that the KE0 beta, that expression where the SE of x, did you write anything? Oh, okay, sorry. Something just displayed on the screen which wasn't showing me before.
Oh, I see. Okay.
Last integral.
Good. You can see that now, right?
Yes, thank you.
All right. Very good. So what we'll do next time is pick a specific expression for this V of x and insert it into this path integral, calculate this guy, take its log, and calculate E naught from there. And what it will do is give us a correction in lambda, again, the coupling, to the harmonic oscillator ground state. Okay. Great. All right. I'll see you guys on Wednesday.